Today we're going to talk a little bit about geothermal. Sort of just an introduction. I'm really not here to sell you a product. I'm more here to tell you about how the technology works and some of the touch points that we find are important in doing this particular technology. So the EPA back in 1993 said that the following things about geothermal heat pumps. Now this is three generations of geothermal heat pumps ago. They are the lowest cost heating and cooling of any device on the planet Earth today, and that is still absolutely true. They are best for the air environment. Zero carbon at the place where you're running the equipment. Now, I'm going to use electricity to do that, but I'm going to use as little as 20% of what I would otherwise use as far as total amount of electricity to develop that amount of heat. We'll talk more about those details. So even if you're burning tires in Pennsylvania for part of that electricity, you're not using anywhere near as much electricity to deliver the same amount of BTUs to the space as you would, let's say, with a resistance heater, for example. And then best for the electric utilities. Well, one of the reasons why NH Co-op, by the way, one of the best rebate programs in the country for geothermal, will give you a check, the homeowner a check for up to $10,000 for doing a geothermal retrofit. Is because what you're doing for the utility is you're killing peak load. They have 365 days of service they've got to provide to the electric using public. And the really tough part of the year for them is those 5 days at the end of August where from 1 p.m. to 5 p.m. everybody's running their air conditioner. So that's what we would call a peak demand. I don't know if you talk about that in your course here, but that's something that you pay for in the form of electric rates because, gee, they might say, well, we're using this many kilowatts on the average day, but boy, we get into the late summer, I double that. So they've got to have contracts for delivering that extra electricity during that peak demand. They've got to have more bricks and mortar. They've got to have more generation. They've got to have more distribution. So those are the things that drive up the electric rates most dramatically. Well, when I use a geothermal heat pump, on the coldest winter day, I'm losing BTUs faster than ever out of that envelope. On the hottest summer day, I'm gaining BTUs faster than ever on that envelope, and I need to manage those. But the heat exchange by which I affect that envelope remains constant because the heat exchange in a geothermal heat pump relies on the 50-degree temperature that is the case all day, every day, year-round. So yeah, I'm going to run longer hours on that peak summer or winter day, but my heat exchange is not going to be fighting dramatically high temperature outdoor air or dramatically low temperature outdoor air to make that heat exchange like an air source heat pump does. It doesn't make an air source heat pump bad, it's just very different. And one of the biggest benefits of geothermal is that I have that constant heat exchange medium. All the details by which I'm making my heat exchange and developing the space conditioning is a lot more baseline, if you will. Okay? So that's good news for the utility because they say, well, look, on the coldest winter day, I've got a nice even base load now because I've got all this geo in this area. And on the hottest summer day, boy, if everybody does geo, I'm going to cut my electric load in half during that peak period. Again, making for a nice, smooth slope throughout the year, and at least on paper should drive down electric rates. We won't get into the politics. So, heat pumps are all around us. I don't need to talk too much about students in this course about that, but we all know that everything in nature is always making a heat exchange. Hot always goes to cold by nature. How tight we make the envelope, how big the envelope is, a number of other features surrounding the envelope's effectiveness will slow down or speed up that process. But either way, hot's going to cold. So if we look at a refrigerator as a heat pump, that's what it is, it's a refrigerant circuit, and we say, okay, well, the inside of the refrigerator is not made cold, it's had the heat removed from it. And we know the second law of physics is I cannot create or destroy energy, I can just move it from one place to another. So I put my Budweiser in the refrigerator, I come back a couple hours later, it's 50 degrees when I put it in there, I come back, it's now 35 degrees. So where did those 15 units of energy go? Out the back, where the cat hair collects, right? It's always nice and warm back there. So the compressor circuit remove that energy from the bottle of beer, not very warm, but warm relative to very cold refrigerant, out of the body of the refrigerator, and in this case into the kitchen space by way of a heat exchange. And you guys are familiar with this activity. So what we want to do is we want to use as little energy as possible to run that circuit. And it's really an aptly named device. It's a heat pump. It doesn't heat up. People say, I get it. You bring in the 50-degree water and then you heat it up to 70, right? No. I bring in the 50-degree water, suck 6 or 10 units of energy out of that water, and then deliver it to the space over and over and over again using this circuit. This circuit, in the case of a geothermal heat pump, is include a well pump or a loop pump, the compressor itself, and the delivery mechanism. So that device, that set of devices, is my heat pump system. What I want to do is I want to minimize the amount of energy that I need to use, in this case electrical energy, to run that machinery that extracts stored solar energy in the winter and that stores unwanted solar energy in the summer. That's it. They're not very sexy. They're very quiet. They're all inside. But if you can't wrap your head around a refrigerant circuit, or you don't find it to be particularly appealing, it's dramatically efficient, but it's not going to make you that excited otherwise. So we know what a ton is. Everybody knows what a ton is. 12,000 BTUs per hour is 1 ton, and it was identified initially as a cooling measurement, meaning if I have a 1 ton capacity need inside a building, that means I'm gaining 12,000 BTUs of unwanted solar gain per hour, and I need a device, a 1 ton device will remove that ton of unwanted heat per hour. So that when we talk about a ton, I'm not talking about 2,000 pounds, I'm talking about 12,000 British thermal units. Here in the U.S., as we bastardized pretty much everything else, we've bastardized the term as well. We don't only use it for cooling, we also use it for heating. So if I have a 5-ton house, that on the coldest winter day, on a design day in Laconia, let's say, then I have a dwelling that on the coldest day is going to lose 60,000 BTUs per hour, and so I need a device big enough to replace that 60,000 BTUs I lost. So when I talk about a ton from this point forward this afternoon, that's what I'm talking about. And by the way, the reason it's called a ton is because what a 12,000 BTUs is the amount of heat energy that it takes to melt 1 ton of ice. So that's where the term originated from. And I'm sure you're all about BTUs at this point in your course with Wes. So, some housekeeping to get out of the way. So everybody knows heat pumps don't work north of the Mason-Dixon line. Well, maybe that's not so true anymore. The generation that's in front of me might even not have ever heard that. Well, we know that air source heat pumps even are now quite popular because although they're not particularly efficient when I have a big heat exchange with that outdoor air, they are capable of running in very cold environments. And so now we're starting to see those ductless splits come in. I'm sure you guys are playing with those as well. So basically scroll compressor technology, modern scroll compressor technology, which is very low friction. And now even as we speak, digitally commutated compressors are coming out, which allow for varying speeds of runtime, which can really increase efficiency, are really coming online. And not only that, when we talk about a geothermal heat pump, we're talking about a heat pump system, as I mentioned earlier, that's doing the work from a source of constant earth temperature, not declining or increasing outdoor air temperature. Really, that's the only difference between the two mechanisms, okay? So we know that the earth itself is really a heat soak. Underground, 50 feet down or so, here in town, it's about 50 degrees, year-round. And you say, well, that's interesting, 50. Why magic 50? Well, if you think of it, the typical coldest temperature is about 0. And the typical hottest temperature is about 100. So the Earth really is like a heat soak. It represents sort of a median annual temperature. That's really all there is to it. And when we talk about geothermal HVAC, We're not talking about that deep earth geothermal where they drill down 5 miles and they pump water down and it blows back up steam and they run a turbine to make electricity. No, that's deep earth. That's the magma in the middle of the earth that they're exploiting to do that power generation in that form of geothermal. That's not what we're talking about here. This form of geothermal is about stored solar energy in the near earth. Okay? So when we drill really deep holes, 1,500 feet deep, let's say, down in Manhattan for a commercial project, as I get down below about 500 feet, I start to pick up a little bit of deep earth heat. I might have a source temperature at 500 feet of 50 degrees and a source temperature at 1,500 feet of 60 degrees. So I can get some effect from that, but as a rule, we are not talking about any deep earth effect as far as ground source heat pumps are concerned. In fact, the other great thing about geo, if you really think about it, that heat soak is really that free solar battery. One of the big problems that we see with PV is that batteries are dirty technology. It's all that silicon, all those other things that are involved. Whereas if I'm using a heat pump to get rid of the stored solar gain, and I have an enclosed circuit like a closed loop or even a standing column, then I'm storing that unwanted solar energy in the ground. At the end of the summer, I might have heated up the ground a couple degrees around that well field or that loop field, but then I'm going to switch to heating. And I'm going to get a bonus in the first month of heating. Same is true at the end of the winter, where I probably will cool off the earth around that loop field or well by a couple degrees. And then I'm going to change to cooling. And I'm going to get a bonus in the first month of cooling. So that annual effect can be very dramatic. And in fact, as I'm engineering a larger system, depending on my load heating and my load cooling, I can actually create some economies in that earth coupling based on that fact. So a lot of design goes into that, and if we do that right, we can do a lot with it. But one of the great things about all this solar gain is that the amount of solar energy reaching the surface of the planet is so vast that in 1 year it's about twice as much as will ever be obtained from all the Earth's non-renewable coal, oil, gas, and mined uranium combined. But we feel like we still got to burn stuff, right? You remember Ready Kilowatt? Anybody here old enough to remember Ready Kilowatt? Well, he's really not a bad guy. I mean, if you think about the energy in a kilowatt in resistance heat, like an electric rod in a hot water tank, or a heat pack in the ductwork, or a little disc furnace like you buy at Home Depot, that is a 100% efficient device. Meaning I buy a kilowatt, I get a unit of heat. Okay, that's a 1-to-1, that's a 100% of COP. Here we go, another acronym. Coefficient of performance of 1 means it's 100% efficient. So if I have a 90% efficient furnace, okay, or even a 95, let's say, by the time I figure my stack loss, my flame conversion, and my electric parasites, because again, I've got an actuator, I've got circulators in those systems too, then I'm probably looking at an installed efficiency, if I know what I'm doing, somewhere between 0.7 and 0.8 COP. Now, a therm of natural gas compared to an electric kilowatt, boy, that electric kilowatt costs a lot more. Probably 3-to-1 as far as the amount of heat energy in that mass, or in that asset, if you will, in that energy asset. So when I talk about a geothermal heat pump, I'm not talking about buying a kilowatt to get a unit of heat. I'm talking about buying a kilowatt to run the well pump, the compressor, and the delivery mechanism. And that system, if you will, is going to deliver the 1 kilowatt I bought and extract up to 4 additional kilowatts of stored solar energy out of the ground, delivering up to 5. In fact, today, with digitally commutated compressors coming out on this technology, COPs of up to 5.9. So by buying 1 kilowatt, I deliver almost 6 units of energy. That's the difference. And even down in Massachusetts, where I'm paying 18-20 cents a kilowatt hour delivered, and I've got real cheap gas, say $1.20, $1.30 a gallon, natural gas. I beat that number because of the multiplied efficiency of this mechanism. And in fact, as all energy goes up in cost over time, the mechanism is what makes the whole thing shine brighter and brighter and brighter and be more and more efficient and pay back faster and faster. Because again, yeah, electricity is going to go up in cost too, just like all those other fuels. But because of the multiplied effect of what I do with that kilowatt, that's why Geo is the big winner and will continue to be moving forward. Okay, so we talked a little bit about COP and EER. So we know that what we're looking at here is a device that's up to almost 600% efficient. I'm going to use 5.1. That's the last generation of dual-speed water-air heat pumps. And then let's talk a minute about cooling, too. Now, in cooling, on an air source heat pump, we hear the term SEER, right? Seasonal Energy Efficiency Ratio, and that's a measurement of cooling efficiency. And in fact, those ductless splits that we see out there today have SEERs as high as 21, 22. Pretty good. And again, they're enjoying that because of the recent advances in compressor technology, as is Geo. Okay? But we will never hear the term SEER relating to geothermal, because instead we're going to use the term EER instead of SEER, because there's nothing seasonal about the source temperature a geothermal heat pump system employs at that constant 50 degrees. In fact, you might also see on that air source heat pump of today that what they will do is they will try to annualize the SEER so that it can be identified as an EER. They'll say, well, you know, we're going to have so many days way down in temperature, so many days way up in temperature. So we'll sort of look at the annual federally approved summertime to see how many of those days I'm going to be operating way out of the scope of my most advantageous heat exchange because the air's so hot and humid. And they'll annualize that. And a 21 SEER is annualized to about a 13.5 EER. So let's compare that 13.5 EER of an annualized air source heat pump to COP's last generation of 31.7, excuse me, EER of 31.7, next generation 60, EER of 60, as compared to EER of 13.5. Wow. And why is that? It's all about delta T, right? We know that the further I go from point A to point B, the more energy I use. That's all there is to it. So real quickly, top quality oil or gas furnace, call it 90% efficient, or 0.9 COP. Pellet stove, again, about 0.9 COP, before we talk about stack loss and circulation. Electric resistance is 100% efficient. Problem is, here in New England, a kilowatt is really expensive. Okay? Air source heat pumps annualized, you know, the best COP that these guys have been able to post is about a 2.5. So I want my dwelling to be 70 degrees. That's ASHRAE's set point in the winter, right? When the air outside is 70 degrees and you want the air inside to be 70 degrees, you're operating at a COP of 2.5. But as that outdoor temperature goes down and my delta gets longer, the efficiency of this unit, no pun intended, goes out the window. Okay? It's going to change because I'm not working in that psychometric chart in my most favorable position. Okay? And now these devices, these compressor-based refrigerant devices, are looking at that sweet spot, right? I've got friction in that motor. I've got friction in that blower housing and in that airstream. I've got friction in that water pipe. I've got friction in the motor from the well pump. So all those, I mean, you could suggest that, okay, I could have a COP of 50 if I really looked at it. But because of the frictions in those mechanical devices and the pressures in that activity stream, if you will, I'm really looking for the sweet spot by which the unit is going to operate in its most comfortable and most effective position of temperature and pressure movements. So when I depart from those, let's call them laboratory conditions, I start to diminish my efficiencies directly. And you might have heard of friends that say, oh, my friend put in one of those geothermal systems, but it's not that good. More likely than not, the pipe's too small, the earth coupling's too small, the pump's too big, the dwelling's heat loss calculation was not done responsibly, and I'm trying to heat 10 tons of space with a 5-ton heat pump. Maybe I'm bringing on an electric resistance heater. That's crazy. Even during a peak period. That's like eating salad all week and then having a big tub of ice cream every weekend. You're using the least efficient device, both electrical, to supplement the most efficient device. Kind of silly. And a lot of people say, well, gee, for 20, 30 days out of the winter, why would I buy that extra ton? My house is a 5-ton house, but I'm going to put in 4 tons, and I'm going to run a lot more full-time run hours with that 4-ton, and only on a handful of days in the winter will I need something else to make up the difference. Well, if you got a wood stove, a pellet stove, or a rabbit on a wheel, or you put a sweater on, fantastic. Even if you do use electric resistance heat to make up the difference, okay. The problem is I can't see where the geothermal lets off and the space heater picks up on my electric bill. So I say, oh, I got this electric bill, it's really high, spinning the meter off the wall come January and February. I thought this geo was wonderful. Well, it is. You're not running geo. You're running a space heater. So we see a lot of that, particularly up here in the Northeast. Down in the South and in the Midwest where they make these things and they've got, way more hours of heating, of cooling than we do. We have heating, they've got cooling. Well, what do you supplement air conditioning with? More air conditioning, right? But up here, we pay a lot for a kilowatt. We got a lot of hours of heating. This is something you have to pay very close attention to if you want to have good, successful projects in New England. So, one of the other things I'll leave you with today, worth writing down, I don't think it's not on test, is if you want to look at the efficiencies of these systems and you really want to look at apples to apples, everybody and their brother is going to post the most efficient, the most advantageous numbers they can because they want to sell you their heat pump. But if you go to www.ahridirectory.org, then any unit of any type, a heating and cooling mechanism, that has been rated by the American Refrigeration Institute and the International Standards Organization, their efficiencies will be there. And the good thing about looking there is that they're going to use the same brine temperatures, the same water temperatures, the same refrigerant exchange temperatures. They're going to really have an apples-to-apples environment as they show machine to machine, which is, I think, critical. And we'll see why here in a minute. The same is true for cooling. Make sure you look for that AHRI directory information. And if the people that you're looking to buy the unit from can't say it's here, go here and find it, then it ain't. And you can even be careful. A lot of times the nomenclature will say, we rated this unit using the AHRI method. Well, that ain't the AHRI method. We use their method. Beware and be conscious of that.